Welcome back. So we made it to chapter 12. Chapter 12 is important because here we get to use everything we have learned so far. One of the latest things you learned was how to decide if a molecule was polar or not based on the electronegativity of the bonds and the shape of the molecule based on the Lewis structure, right? So, how can we use that to understand the world around us? You are gonna be amazed about this. So to get to that point, we are gonna cover some objectives, and the first one is gonna be understanding the properties of solids and liquids, and see how that relates to the atoms and molecules that make them. We're going to talk about surface tension and viscosity, which is gonna depend on intermolecular forces. We're gonna see the process of evaporation and condensation and the energy or heat associated with it. The same thing we will do for melting, freezing, and sublimation, which are changes of phases from gas to liquid, from liquid to solid, from solid to liquid, from liquid to gas, from solid to gas, from gas to solid. And we're gonna see how the intermolecular forces, which are dispersion, dipole-dipole, hydrogen bonding, and ion dipole, compare to each other. I will actually we'll be talking about that earlier on the chapter so we can understand everything better. And then with that, we're gonna see how the intermolecular forces depends on the compound that is involved. And with that, we will be able to determine melting points and boiling points. And we will also talk about crystalline solids and the different patterns that they follow. And then we will talk about water, which you already saw on one of the group discussions we did. So let's begin with this, defining the properties of solids and liquids and see how they relate to the atoms or molecules that make them. But, like I told you before, I would like to talk about intermolecular forces first. I think this is important early on the chapter and not later, like the author decided. So, what are intermolecular forces? Well, based on the word itself, intermolecular forces is going to be an attraction that happens between molecules. So, for example, if I have a water molecule, which we know is going to be bent and polar, we are not talking about the force that is holding these two atoms together. That's not what we're talking about when we talk about intermolecular forces. That's what we call a intramolecular force because it's inside the molecule. So that's not the one we're trying to understand. The one we're trying to understand, which is the intermolecular force, will require two molecules. It's between molecules, intermolecular. And this is the part where the previous chapters becomes really important. In the previous chapter, you learn that because hydrogen have an electronegativity of 2.1 and oxygen have an electronegativity of 3.5, when you subtract those two electronegativities, you get a value of 1.4. And we know that anything bigger than 0.4 but less than 1.8 is going to be a polar covalent bond. You learned that on the previous chapter, which means the electrons that are here are being attracted more to the one with the higher electronegativity. So you can see this like a bigger density of electrons closer to the oxygen. The same thing happens over here. The same thing is happening on this bond. Most of the electrons are going to be closer to the oxygen, which means this more negative. Therefore, these parts become partially negative, while this one becomes partially positive. So we learned that on the previous chapter. So the fact that one of those bonds is a polar covalent bond does not mean that this molecule is a polar molecule. That's not what determines that. What determines that is that there's a force pulling the electrons that way, and there's another force. So you have to consider all the forces that are involved. And when you consider those two forces, there's one pushing that way and another one pushing that way. So those two forces are going to combine for an overall force that goes toward that direction. That's why we say that this molecule have partially negative to one side and partially positive to the other side. So all that we learned on the previous chapter, and just reviewing a little bit. So let's take out all this information that we don't need anymore. So we know water is a polar molecule. So partially negative, partially positive. And if you notice, there's a partially negative in close proximity to a partially positive. So this here, that interaction between those two molecules, that's what we call an intermolecular force. The attraction between the partially positive of one molecule with the partially negative of another molecule. And that intermolecular force, we call that a dipole intermolecular force. So I'm going to start using IMF for intermolecular force. So why do we call this a dipole? Well, look at this. This molecule, let me do something here. This molecule here is interacting through an intermolecular force with that other molecule there. But this molecule have a partially negative pole and a partially positive pole. So this molecule have two poles. And what's another nice way of saying two poles? A dipole. So a water molecule is a dipole because it has two poles because it's a polar molecule. And this one is also another dipole. So what better way to call this intermolecular force than a dipole interaction? It makes sense. So that's what we call a dipole interaction, and that's just one example of one of the types of intermolecular forces. So I'm not going to go any deeper into intermolecular forces. We're going to save that for later. But now you have a pretty good idea that an intermolecular force happens between two or more molecules, and is due because of the polarity of the molecules or other things that we're going to talk about, but depends on the properties of the molecules. And why are intermolecular forces important? Well, remember when we had the group discussion that I asked you to go to the sink and look at the water, and some of you told me about the cohesiveness of water. Some of you told me about the surface tension on the water. So all that is due to intermolecular forces. The reason why is you have a glass container. Let's say you have a glass container like that, and you put water in there. The reason why the water doesn't really look like that, the reason water on the glass container is going to be something like that with what you already know about the meniscus is because the water is being attracted to the glass. The water is being attracted to the glass, and the water is being attracted to the water. So it's pulling down to the water while it's also being attracted. That's why it creates a meniscus. And all that is because these two waters are being attracted by an intermolecular force, which is going to be a dipole-dipole because water is a dipole and the other water is another dipole. And the ones that are going up the wall have also a dipole interactions between the water molecule and the molecules from the glass. So intermolecular forces are going to be really important because they're going to allow us to understand the things we see. How come an insect, like a fly, can land in top of the water and doesn't sink? It's because the water molecules are being attracted to each other, and the weight of the mosquito is not strong enough to break the attraction between the waters. It's like having a trampoline where you jump on it and it can hold you without breaking because the forces keeping the trampoline together are very strong. And imagine that happening between molecules, and that's what we call intermolecular forces. And that's what's so important that we understand intermolecular forces. So, knowing now what you know about intermolecular forces, which is attraction between molecules, what determines whether a substance is a solid, liquid, or gas? Well, let's say you have a collection of molecules and you have a collection of molecules like that. And if this collection of molecules have very strong intermolecular forces between all of them, so these are the forces keeping those together, and they attract each other. If you really consider all those forces keeping all those molecules together, you will say that those are very strong. So when the intermolecular forces are very strong and they happen to be on a way where they can feel the forces from everywhere, most likely this would be a solid because the forces keeping those together are going to be so strong that the solids are barely going to be able to move around. And that's what a solid is. If you touch a solid, you don't feel it moving around. It's just fighting against you. It doesn't want to move because the molecules are organized on a very nice way. And if this pattern that we just have in here happens to repeat and repeat and repeat and repeat and so on and so on and so on, then this is a very well-defined solid. And this is what we're going to call a crystalline solid because the forces reflect all over the same over and over and over and over. There's another type of solid which is not going to be as that. Imagine that instead of having that, you have a solid like that, but then on the other side, you have something you have something like this. And then on the other side, you have something like that. At this point, you can start seeing that there's an attraction there. There's an attraction there. The attraction here is kind of different. There's an attraction here, there. So the same structure you have before is no longer the same. So the forces are going to be very different. Like this force is very strong, very close, while this one is very weak. So there's not a pattern. You don't see a continuous pattern repeating how the molecules are arranged. So it's still a solid because they're trapped in there, but we're going to call this an amorphous solid. And imagine this. I imagine all of you have seen a diamond before. A diamond is very well defined with very neat lines, very crystalline structure, and it's super solid. That's what we call a crystalline solid. And now imagine a piece of coal, like the one you put on your coal barbecue. It's a solid, but if you hit it with something, it's going to crumble because it's kind of amorphous. It's not as the diamond. So having an amorphous solid most of the times implies that the strengths within the atoms or molecules are not that strong. So that's something we can say about the solids and how we can determine based on the atoms if it's going to be a solid or not. What about the liquid? The liquid, you know that if you have water on your on a bottle and you turn the bottle around, the liquid moves with the bottle. It tends to fill up, it tends to level. So on the liquid, you're gonna have the molecules as before. Well, they're not gonna be as arranged, neatly arranged like on the solid. And the attractions that we're gonna see between them are gonna be weaker than the solid we had before. And when we study the intermolecular forces on detail, you're gonna see that some of the intermolecular forces, depending on the molecules, are gonna be very weak. Others, depending on the shape and polarity of the molecules, are gonna be very strong. So on the liquids, the forces are not as strong as the solid, and they are flexible. They tend to do like the ocean. So that's why you have a liquid, when you put it on a container, it takes the shape of the container and it fills up as much as it can. What about the gas? Well, the gas is a whole different story. On the gas, you're going to have the particles, and as you learn on the gas chapter, the particles are going to be very far apart. And they're also moving really fast. So, and according to the kinetic molecular theory of gases, the particles tend not to interact with each other. So they're so far apart that is there any intermolecular force, it's going to be very weak because they're going to be so far apart. So the gases are not going to have like a feeling where you can touch them because they're so far apart. You basically go in between the molecules. They also, since they're moving so fast, if you put gas inside a bottle, before you know it, they're going to spread through the whole bottle and they're going to fill up the bottle. The bigger the bottle, the lower the pressure. You knew that, right? So the gases are going to be different on that regard. The particles are going to be very, very far apart, and it will take the shape of the whole container where you put them. So that's a way to understand solid, liquid, and gases. And make sure you look at your textbook for better drawings on, that tells you more. So with that said, talk about the properties of the liquids. I didn't mention many of them, but you can check the textbook and the posted PowerPoint. And also just kind of summarize what I said about the properties of liquids in terms of the atoms and molecules that compose them. Remember to talk about intermolecular forces. After you do that with the liquids, go ahead and do it with the solids, and also go ahead and do it with the with the gases. We did a whole chapter on it. So talk about what a crystalline solid is and what an amorphous solid is. You're basically kind of putting on your own words what I just discussed few minutes ago. And once you're done with that, we're gonna say that we have discussed some of the properties of solids and liquids, pending that you're gonna be the textbook or look at the posted PowerPoint in Canvas, and we can relate those properties to how the atoms and molecules are distributed within the solid, liquid, and gas, which is gonna be based on their intermolecular forces. And I understand we haven't discussed much about the intermolecular forces, but kind of paraphrase what I said in your own words so you can own that understanding. And with that said, that's the end of our first section for this chapter. When we come back, we are going to talk specifically about some of the properties that we observe that are going to be due to intermolecular forces. So see you soon. Take care.